I think so.
And now you can be heard.
Great.
Wow.
And be seen,
Hello.
hopefully.
Seen soon, yes.
Seen soon.
Nice.
Webcam, whoa.
What?
No, we'll just
Whoa.
put you in the
Whoa,
light.
that's such a nice room.
Did you literally just hype your own room?
Here you
Alright,
go.
thank you.
On the right now.
That's
And you
great.
can see chat.
I am
Great.
blind, so yes.
Wow. Are you from Ireland?
Yes. Zijn er al mensen?
Are there
Yeah, maybe we should wait a bit.
Yeah, of course.
Like,
check.
wait.
Yeah, Liliana still needs to post it.
Oh, okay.
No, this is chat characters.
Oh.
Where are people?
Concurrent viewers.
Two.
Two.
Which is
Aww.
probably
cute.
us.
That's
and
us, yeah.
That's definitely us.
Yeah, but Lilia's still posting the link, so it should be
Because
fine.
I'm watching it as well. Let's click that.
Oh, we're
away.
very delayed. Nice.
Whoa, yeah.
No, it's not that much. I think. Okay.
I mean, it's fine.
Oh, here. So now you have a mouse and
Great.
that is it.
Great.
Great. So if I do this, it can be seen.
Oh, I don't see anything. Actually.
No, but
oh,
it's delayed.
oh, yeah, it's a delayed. That's a bit ghetto.
Hmm?
No, it's fine.
I mean, just look at the right.
Yeah, no, we do. Okay.
So it just takes a while until we see the questions.
Yeah, and they haven't joined
Nice.
yet because
Yeah,
No,
there's someone in
no,
the
there's
chat.
people coming. Howdy.
Oh, howdy.
Oh, there it is, finally.
Okay, we're very delayed. Nice.
Yeah. Oof.
Okay, so we wait till a little bit more people are joining, I guess.
Yes. Gezellig.
Yeah, man. Still one people in the chat only.
Ooh.
Oh, 2 people now. Nice. Oh, now we're waiting for the link to go online.
Right.
Oh, Shani is already posting it. Cool.
Nice. In here.
Oh, Arnes also. Okay.
Nice, okay.
Then
So
we
they should be
wait.
coming now.
Yeah, I think so. All right. Oh, I think more people are coming.
Ooh.
Nice. Let's wait a little longer.
Yeah.
Okay. Yeah.
Oh, did it just people leave?
Is this concurrent?
where do you see-
Chat replay back? Would it be possible to go through one of the person, or is this more or a specific Q&A? I feel like if we have enough time, we could probably do some exercises from the question exams or the practice exams. But let's first see if people have more specific questions. Also, I feel like we are a bit delayed, so I think the chat is also a little delayed, but you know, it should be fine. And let's wait a few more seconds to see if more people are joining or not. Because I think we only have 8 people right now. 11 people.
Yeah, where should you look?
There or
Oh.
here, I guess.
But it's 2 different numbers.
We are very much delayed.
Oh my god.
Can I check? There shouldn't be much of a delay.
It's like a very
Oh,
long
maybe
delay.
it's only for us or
Oh.
something.
Or maybe just very slow.
Oh, we're back.
It
Okay.
says
you're
excellent
still
connection.
you're still live. Don't worry.
Oh,
People
okay.
can hear us.
Cool.
I don't think we have a chat delay.
I mean, no, but like in the screen here.
Or do we
It's
just see
very
our
much so.
stuff
All pretty
later or
stable.
something?
Okay. No.
Nice.
Then this is the best we can do.
Okay.
Okay, well. Oh. Wait,
Aw.
Noodle King, isn't that Arjan? And if so, pressure.
Data leak, just spoil his online nickname.
Sorry. Could show how to determine if something is an alias, like problem 12 from example exam 18. Did you do that one?
I don't think so.
We can look it
No,
up.
I did the one that I...
Okay, let's start then in a bit, because I think there are some people joining. Let me see if I can go to the assignments.
Yeah. So everything on that screen is what the screen
Is what
also
they
sees.
see.
Yeah.
Okay.
Okay.
Yeah,
So
you can just
first
drag it.
look,
Right.
or first
Right,
find the
right.
assignments.
Let me look up the exam 18. What's your screen? Who's given name? Crash course. Fair. Let's go to the exam then, Max. We can check it. All exams.
I think I did...
This one. Yeah, this
I
is
did
the one,
the
yeah,
21, I think. Let me
I
check.
mean, we can look at it and see if we understand it. And then problem 12. Right. I think I know how this went. Laura, far as I know, chapter 14 wasn't exam material, right?
No, I don't think so, but I can check for a second.
I think it wasn't.
Yeah, oh wait, you can see it in treated material, I think.
Yeah, you also have on Brightspace, you have the under contents and then treated exam material. You can exactly see what the material was, but last year it wasn't exam material, so I don't think it will be this year either. Also, Max, I'm still looking up your questions. Give us a second. Let me. Can I drag it then?
Yes, to the right.
Ooh. Oh.
Go.
Oh.
And now
Interesting.
just, yeah.
This is not my laptop too,
Maybe
so I'm a
you
bit slow.
scroll to the bottom. Or
Oh, yeah, you
to
can
the right. Yes,
Oh.
there.
So it's...
Like this?
Yeah.
Well, if you scroll more. Oh no, wait, go up. At the top right, the little present thingy.
This.
No,
Oh,
below
this.
that one, yes. Then it's full screen.
Ah.
Oh, I didn't know that.
I never use it. Alright, so let's see what happens. Yeah, so you had a formula for this. Let me just look it up real quick, because I don't know all of them by heart.
Here.
Yeah. Oh,
Can you read it?
no, I'm blind.
Aliases.
Wait, can you write it down else? AP, go ahead.
Yes. Okay.
Because this
Wait.
is the formula.
If we do...
Where?
Yeah, can you...
Oh, wait.
Sorry.
That one.
Ah,
There
okay.
you go.
Let's see.
Thank you.
Wow. Oh, this is easier than Paint indeed.
Oh, it's this one, right?
This.
Oh, yeah. It's the same. Yes.
This is just gonna be the whole Q&A. It's just us writing stuff.
I mean, it's fine.
Yes.
I seriously need glasses to read your... cheat sheet.
Damn. And another one, which is basically the same. Oh, whoa. Okay, this is trippy. And then... Oh. And minus pi. So it's one positive and one negative.
Yeah, so these two are the formulas for the aliases. Yeah, thank you. Let me see. So now, wait. So where's the? Wait, Thomas, help.
Oh, top, I think.
Alt, then tab.
Oh, yeah.
I know
Smart.
how computers work.
Sorry.
Okay.
I don't.
All right. So if you have to find aliases of this cosine here, what they do is according to oh, sorry guys, I'm a bit slow. So what they do is they sort of bring the n outside of this, so that's sorry. Yeah, so that's this step here. So they basically bring the n out of here and add the minus 2 pi. And then they work this out further and simplify it. So yeah, that's basically, yeah, it's just following this formula. I can't really make it any more special than it is. I don't know, Max, if that sort of answers your question. Okay, let's wait for that in a bit. Okay, so it's undertreated material, Laura, but I think it's treated in the class, but I don't think it's exam material. You can double check by asking the lecturer, but I don't think it is. So, you know.
Yeah,
I think-
at this point I would like email just to be sure, because now I'm also insecure.
No, I think it's not under the
Yeah.
exam material, but you can ask him, and then
Yeah.
you know for sure.
I didn't watch the lectures, so.
Also, for people who ask me whether graphical calculators are allowed, I just got an email back from the lecturer, and they are in fact allowed. So you can bring your graphical calculator to the exam. In case they're going to make a point of it, because I remember last year that it was also allowed, but then during, like, 5 minutes before the exam started, they sort of came in, and then it was...
Yeah, it was like, what happened last year was that they said it was allowed, and then I only brought a graphical calculator,
Yeah, and then
suddenly they said that it wasn't anymore, but I think it's just because those people are just used to graphical calculators never being allowed. So I would, just to be sure, bring a
both.
normal,
Yeah.
bring both.
But
So
they
you're
are
not-
allowed.
So you're not stressing.
Yeah, but they are in
But
fact
they
allowed.
are allowed, so yeah. You can just throw that back at those people in the exam hall.
Oh, Arjan just also confirmed chapter 14 is never exam material, so nope. It's not exam
okay.
material.
Okay,
so you
that's
don't have to
great.
worry about that.
Awesome.
Another question, basically just fill in the formula. Yeah, okay, cool. Max, yeah, it's literally just a formula. Yeah.
Yes, cool.
Are all recurrent states absorbing? Do you know that by heart? Because I know.
Well, absorbing is just one state, and recurrent can be an entire
That's
group,
true. Yeah,
group
you're
of
right.
nodes.
Yeah, so Lara, to make it sort of a better extension between the two, recurrent states can be like a cluster of states that are all recurrent, whereas an absorbing state is always one state that only has errors to itself, right?
I think that is true.
That's how I always remembered it, so yeah. Could you explain slide 9 from lecture 10, how to get the gain and the phase? What we can certainly try. Let me go this.
Oh.
No, that one, yeah.
This one, right?
Oh yeah, because it was.
Yeah.
If you go up with your mouse,
Oh.
just push up
Oh no,
to
it's
the top
slow.
of the screen. Oh, never mind, it's just slow.
What the hell? Push up.
Oh, it doesn't show.
Thomas, your laptop is weird.
No, it's not. This is Windows.
Right to
Every
that.
laptop can do this. That's all I'm saying.
Oh.
Right, I'm sorry. Anyways, slides.
Guess we're just dumb.
Yeah.
Which lecture was it?
Could you explain slide 9 from lecture 10, of course? Or at least I hope so, because sometimes he writes very intricate stuff on his slides. 4, 5, 6, 8, 9. Alrighty.
Okay.
And then the phase and the gain. Let's see.
Maybe click the percent again.
Ah.
So we get this.
Yeah. Let the frequency response from LTI system be this, and consider the input. Like computer outputs using since the frequency of X is equal to. We have to evaluate. Yes. So the gain is. Yeah. So basically, the gain is always the absolute value of your what's it called, frequency response. So in this case, you know that what your the frequency response, right? Yeah. Yes. So you know that if you fill in 37 pi, you will get 2 over 1 plus I. So you take the absolute value of that, and well, the absolute value of 2 is 2, and the absolute value of 1 plus I. Then you have. So if we go back to the drawing board, yeah, you know that the absolute value, or in other words, sort of the length of the vector, so of a complex value, is the same as the square root of a squared plus b squared, which would then be, in this case, I think it was 1 plus I, so it would be 1 squared plus 1 squared, which is 2. And if we go back,
You just have to press one.
yeah. Then you see in fact that the absolute value, or like the gain of 1 plus I is in fact the square root of 2, and so 2 divided by the square root of 2 is the square root of 2. If you don't see that step, please let me know, then I'll explain it as well. And the phase, in this case, you take the argument of, in the frequency response given that it takes 37 pi, and this basically means that, again, you fill in the 37 pi, you get a 2 over 1 plus I, and then you take the arguments, and you can do it like this, but I find this a bit counterintuitive, so what I always do or prefer to do is I convert this to the polar form, because then you can immediately read what the argument is by looking at what is in the power of the exponential. So I think that would make more sense. Is that clear? Since we are delayed, I'll wait for your answer, and else I'll go on. Wouter, can you maybe explain time, frequency domain, and the corresponding formulas?
So, writing from the spectrum to the sum of exponentials and then to sines and cosines. Let's see. Let's go to the syllabus. And then I think it was around page...
Wait, you know the pages of the syllabus?
Yeah, because people ask me questions and then I'm like, it's explained here. Oh, no.
Never mind.
That's not what I said.
Damn, girl. Dedication.
I got exactly at the page where I wanted to go. Oh my god, this is just a special power. Okay, so let's say you start... Oh, Sophie says thanks.
Alright, cool.
That's great. Okay, yeah, then we can start with this. Let's say you start with the spectrum, then you get these values. So the values on top are the A's, and the values here are the F's. And then here they have rewritten them like so. So here's A minus 1 like it's here, and here it's F minus 1. Yeah, here they say minus F1. But that's F minus 1, right?
Yeah, same thing.
Yeah, that's the same thing. And then here, if you want to write from the spectrum to the sum of exponentials, basically, it's just filling this in. So, let's see. So if you have Fn and An, then it comes all the way at the end. And you write Fn in here. And it's times 2 pi. That's why usually... when you write it in the exponential, suddenly the frequency seems to be multiplied by 2. That's because it becomes like not the F frequency, but the W frequency. It's both called frequency, which is kind of confusing. So that's why it's like appears to be multiplied by 2. Yeah, because it is, basically.
Yeah.
And then, you write the AN in front of it, which is usually also another E. So you can...
Yeah, so you can also sort of merge them together still, but you don't quite need to. Also, so take in mind, if you're converting from the sum of all E's to the spectrum, make sure that you sort of distinguish which one is just an E in front of the actual one that contains the frequency. So make sure you get the right one.
Yeah, that's usually the phase. Right?
Yeah.
And then the A is also in front of it. And then let's see the formula of going to the cosine. Oh, here they do it the other way around. We can do it the other way around. So here they go from cosine to the sum of exponentials to the spectrum. So you have the 10 plus 14 cosine with a frequency of 200 pi and one of 500 pi and their phase. So when they write it to the sum of exponentials, they use the inverse formula of Euler. So usually what I do when I write it back to the cosine is also work your way to being able to write it in the, like, convert it back using the inverse formula of Euler, which sounds kind of weird, but it's, So that's why the amplitudes get multiplied by a half because of the inverse formula. And that's how you get this sum. And then let's see. Yeah, so here you see like the double E's. So here the phase and the minus I is there, and then the W frequency is in here. And then you do that for all the cosines. And then if you use like this kind of formula or rewrite method, then you can write it to the frequency spectrum.
Yeah.
Does that make sense, or did I go too fast?
Whose question was this again?
Wouter, I think.
Wouter, is that clear? Well, in the meantime, because we are still delayed, we'll wait for your answer, and else we explain it again.
Yes.
In the meantime, Laura, if you represent a sum of sinusoids in the time domain, why do you take only the real parts of the complex exponentials? Like, why is that allowed?
Chapter 8.
That is this one, right? I believe.
Yeah.
If you represent a sum of sinusoids in the time domain, why do you take only the real parts of the complex exponentials? Or like, why is that allowed? Wait, do you know what she means?
No. Can you elaborate? Because I'm not sure if I... like, maybe there's an example where they do this, and then we can look at it. Nice
we
delay.
wait, yeah. Love the
Actually.
delay. Oh, yes, this makes it
Okay,
clear.
that's
Thanks.
nice. That's
Good,
nice to hear.
Nice,
Okay.
nice. Now we wait for Laura.
Good quality Wi-Fi.
Yeah, love it. No, I think this is always the case with streaming.
Yeah, that's true. We should put on waiting music.
Elevator music. Nice. This is because you only have the cosine. This is because you only have the cosine. Why did you take only the real part of it? You need cosine plus sign to get the E number. Yeah. Arjan to the rescue. I just don't understand the question. If you represent a sum of sinusoids in the time domain, why do you take only the real parts of the complex exponentials?
We can scroll a bit, see if it's...
Oh, like you can write it as x days equals to sum. Oh, like that.
Oh, when you're summing
yeah.
cosines, you mean? Or, yeah, what are we summing then? Oh, yeah, so we're... yeah, oh, yeah.
Yeah,
We're
do you
summing
get it?
cosines with the same frequency.
Yeah, exactly.
So then you pick the real parts, so you don't have to mess with with the whole imaginary numbers, basically. And then you can easier sum them, and then because it's in the real part, when you put it back, it's still cosine and not cosine and sine. So yeah, I think in chapter 7 it's like kind of an algorithm for summing two cosines.
Yeah, I think they gave like a stepwise
Yeah.
plan. It's the same technique as... Yeah, Arjan, indeed, what you said.
Yes. Wow. Oh wow.
Wow.
We're the same mind. Yeah. This is page 135.
Yeah.
And yeah, so it's you just use the real part basically because it's easier.
Yeah, you can
And-
sum it in
and-
real time and then convert it back.
Yeah, and because you convert it back, you don't really need to do it with the whole.
Yeah.
Yeah.
Yeah, I think that's the reason, yeah. So it's because it's only constants.
Yes.
Yeah, exactly. Yeah.
Yeah. So if you were, if the question would be sum these two things and it's a cosine and a sine, then the most easiest thing to do would be convert the sine to cosine and then sum them because it's easier to work with the real part.
Exactly. So also
and
make
they
sure that you sort of know the techniques, like so much sine is so much cosine, how to convert between the two, know the Soska-Stoa rules.
Yes.
And like the...
I wrote that on my cheat
Yeah, and
sheet.
like sine squared plus cosine squared is 1, like these things.
Yeah.
The basic algebra things with the cosine and the sine that you've learned in high school. Put them on your cheat sheet because I think they'll be very
Yeah.
useful, especially for converting sine to cosine.
Yeah,
So-
I think what I did was also first make an example exam, and then after making the first one, I made my cheat sheet so I would kind of know what would be important to be on it, and then I
Yeah.
could make the others using my cheat sheet and not the whole lecture notes. Yeah,
Exactly.
so
All right, I hope that's clear, Laura. Let's now see your other question. Could you explain the geometric distribution theory, because I didn't understand that at all. Like, what do you use them for? Okay.
I think that was in chapter 4.
Yeah, 3
Yeah.
or 4, indeed. Go out of here. Let me go there. Let's try 4 first. I think it's in there.
Great.
Wow.
Wow. So
Alright, let's
good.
consider. Blah, 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 blah. Just a minute, you want to know the distribution series? Yes. Okay. We call the geometric distribution.
Oh, it's a proof.
Yeah, I know.
Yeah.
I'm trying to find like the
Why we use
formula
it.
that we always use. Yeah,
Oh yeah.
because these are all proofs. Do they have an example of what the actual formula is? Because that would be nice.
Is it this?
I think it's this one. Yeah.
Yeah.
Yeah. So essentially, and this one, by the way.
Oh,
So
yeah.
essentially, what they do, why we use it, is if you are going to end up in a state a lot and you can't, for example, move out of it anymore, then you can sort of say, okay, we get a sum of all these states to infinity. We're going there a lot, like over and over again, and it sort of averages out to the following formula. So that's why we use it. I think in one of the example exams, but I'm not 100% sure, there is an example where they do this. Let me see if
Yeah,
I can
there's-
find it.
In one of the exams, it's indeed just a question like write this differently, and you have to use that.
Yeah,
Oh,
do you
yeah.
know which one of these?
Yeah, it's
is?
this one.
The
The last one. Yeah,
IT?
that's the one I did.
Right. Let me go to the answers right away.
Oh, yeah, smart.
And then, yeah, it's this one.
Yeah.
Problem 8. So let me see what problem 8 was. What is the value of the sum? Yeah, so here you see we're going to infinity. We're going to sum this basically over and over again. And we sort of keep doing this. And then if you know that you're going to over and over again sum something, or that's the same as sort of being stuck in an endless loop in a specific state, because that's why you always also use it, then you can make use of the geometric distribution. And yeah, well, that's just a formula. I can't make it any nicer, any prettier. It's just they fill in the 1/5. They say, so we
Yeah,
do it to the
so-
power 2, and then
Yeah.
the I remains.
Yeah, and here, what I do here is because for the geometric distribution, it's from 0
Yeah,
to infinity and not 1 to infinity. So they add the power of 0 to the sum, and the power of 0 is always 1. So that's why you can extend the sum with 0 and then do -1.
exactly. So you just do -1, and then, yeah, it's basically just filling it out, and that gives the answer. So I hope that is clear then. Bjorn asks, could you perhaps give me an example of how I could be asked to use the formulas that are presented on the first page of Span Summary Part 2?
Oh my god, I don't think I have this summary.
I don't have it open either, but
Yeah.
wait, maybe I can check WhatsApp if I have it still. Span Summary 101.
It's famous.
Very good way to study.
I feel like all the second years are just totally just using those, because I did 2 last year.
Yeah.
They're amazing.
I found it already.
The Holy Grail. Whoa.
Great. Okay,
Heck
so
of a-
let me check. I have it on my phone open because this is not my laptop, but let me check. So you ask, could you perhaps give me an example of how I could be asked to use the formulas that are presented on the first page? Let me check what the formulas are. Yeah, so the part 2. So I think you mean the ones that we just went over, so the real part. I think the formulas for the real part are mostly when they ask you sum these 2 cosines together or sum these 2 sinusoids together. what is the answer, like write it in one single cosine, then you can use the formulas for the real one, and the other formulas are mostly used when converting from spectrum to a sum or the other way around.
Mhm.
So I think if you go to the example exams, there are quite some questions that use those formulas, so I would say try and have a look at those, Bjorn, because these are used for that.
Yes.
And I think they're quite important, so I would encourage you to look at those.
Yes. So, an example of how you could be asked to use those formulas is like summing cosines, basically. Yeah.
Exactly.
To conclude.
All right. I hope that was clear as well, Bjorn. If not, let me know.
Nice.
All right, then we wait. In the meantime, I don't see other questions yet. Are there more questions?
We can wait a little bit until.
Exactly, and else we
yeah.
can maybe do some example exams. Because I still
Yes.
saw in the WhatsApp also that people still had trouble converting, for example, from polar form to Cartesian form and back. I don't know if that's clear now for everyone. Sophie. I still don't really understand how the bounds of an integral change when, for example, you have utility over an integral, like on slide 15 from lecture 10 or exercise 10.18d. Alright, let's go back to the lecture slide. Yeah, that's lecture
You can do right click and open a new.
Shh, we don't.
Don't do that in this house.
Let me see.
Lecture
Slide
10.
Lecture 10, slide 15. Could you give an example of working with a t-step transition probability? Yeah, in a bit. Right. This one. Okay. I still don't realize how the bounds of an integral change when, for example, you have ut or ht in the integral, like on slide 15 from lecture 10. Okay, so let's see.
Okay.
Yeah, so here you have ut minus s. Wait, I actually wrote down a useful thing for this. Hold up. Ooh. Here. Looking at my notebook right now. Yes. So, let's see. Is this the same one? Yeah, now I have to check. Oh, what am I doing? So, let's
I can take a picture so you can remember.
Yeah, no, it's fine. It's
Okay.
fine. So here, t minus s is supposed to be bigger than 0 because here you know that for step function it only will output anything that is multiplied with it if what is within the step function is bigger than 0. So then you also know by this thing that is given, you also know that t must be bigger than s. So what we then know is, okay, t must be bigger than s. So here you know, and you also know that t. Whoa, sorry. Now I'm confusing myself. Hold up. I've explained this before. Why did I forget?
Yeah, it's confusing because the minus means.
Yeah, no.
Yeah.
Yeah, and you also know that minus t plus s, I think that's also minus t plus s must be, I think also bigger than 0, but now I'm confusing myself. No, I'm clowning. Never mind. Let's see.
Oh, yeah, because it changes from to infinity to t.
Yeah, no, I know,
Yeah.
but like, why do they say bigger than equal than 1? That's what is confusing to me. So you see, it's quite hard. No.
Yeah, that's the thing with step functions. Let me check if
So with step function, like I said, it should always be bigger than 0. What is inside, and then only then. But wait, no, I think I see it. Do I?
We can start by thinking what this step function looks like.
Go ahead.
T minus s. So s can be anything.
Mm.
But let's see.
Maybe, wait. Let me give a more concrete example because this is not... So sometimes I find his slides very weird. Let me actually
Yeah.
get an example because this...
Yeah, wait.
won't
I
help.
think she mentioned an exercise.
Yeah, so Arjan also said S should be smaller than T, so T is the upper limit. Yeah, that
yeah.
is in
Smart,
fact
smart.
true, but let me give a more concrete example. I think this was assignment 5. Where is the assignment? Jesus.
It's
It's like here, right? And then you click it.
or under content.
No, in content they said which was the assignment, remember? And then
No, but I just want to open the assignment. That's what I...
but the assignments
I'm
that
done.
aren't
I'm done, never mind.
there
We
the
don't-
lecture notes.
Don't speak about it.
Okay. That didn't happen.
Anyway. Yeah, so for 10.12, you can use it as an example. So here, the same happens. Let me just see where... Yeah, so it's here. And they do the same thing. Hold up. Yeah, so what I did, let me just open this again. So at one given moment, you have the integral of infinity to minus infinity e minus as times us times e minus b t minus s u t minus s ds. Yes. And then what they do, what you know, is that this one, since it's also a step function, should be bigger than 0. Here you know that t must be bigger than s, given this rule. So you know that, in fact, t will be the upper bound, because s here must be at least bigger than 0. So you get 0, because that's where you start. That's like the smallest value that s can be. And then the upper limit is t. And then you get e minus as, because this then will always be 1, so you can just multiply it with this one, so it just stays the same, times e minus b t minus s. And then this one also becomes 1, so it's fine, ds. So that's how you sort of know when you can add it to the integral, like when you can change the integral in order to make your step functions fit. We sort of use the step functions now to change the domain of the integral because, so like I said, 0 is the lowest point that you can get and t the highest. So that's how you can then sort of update the integral to fit your step functions. I hope, Sophie, that is clear then. Very good. Laura asks, could you give an example of working with a t-step transition probability? Do you know?
A what?
T-step transition probability.
Wait. Oh, that one. Okay. T-step.
I think it's like... hold up. Hold up. You go back. Slides. I think it's like in the second or third slide.
Ooh.
I believe. I need to go back like this in 3. Let me just look for them. Sorry for late, but thanks for the explanation. No problem, Bjorn. T-step. I think you mean something like this. I love his last slides. Laura, do you have a more concrete example for the t-step transition probability? Because I know it's somewhere in here, but I kind of forgot. Okay. And could you maybe also explain pulse function again? I don't understand how these work with those, like the square and the triangle ones. Okay, well, I'll wait for you to answer the other question. Can you do the pulse functions?
The pulse functions. Well, we can go to the lecture notes.
Do you know the page for pulse
No.
functions? Bummer.
Too bad. Let's see where this will get me. Oh, wow.
Wow.
Beautiful. Let's see. No, I don't think this is what I want, right?
I think it is.
Do we just want the Dirac delta, or?
No, I think the pulse function, so...
Oh,
like
yeah,
when you
yeah,
do,
wait. So
with the sink and the square, yeah, these ones.
yeah, okay. Aha.
Uh-huh. Do you know?
Do you want to do them?
Sure,
I can help you if I can.
No, I know how it works.
Okay.
Two steps in the syllabus. Okay, we'll do that in a sec. So what the pulse function basically does is it sort of helps you to convert the signal that you currently have to a more readable, more sort of processable other function. So, for example, in this function, you see that the pulse is sort of defined as these blocks, but they don't. Okay, wait, I'm distracted by the chat now. So what they do, for example, here is, let me find a good one. Yeah, so for example, they have this formula and they apply it, so that's the pulse function, and then they have another random formula, xn, and that's your signal, and you sort of use the pulse function to make a new signal out of this to sort of process it better. This all looks very intimidating, but it isn't, I promise. Let me just... I think there was an assignment on this, which makes it more clear. I think it's assignment 4, from the top of my head. Yes.
Whoa, big
wow.
man.
So what they do here is... I have to check. For 9.4, where was the actual assignment? Oh wait, it's in the syllabus, right? Yeah. Let me also get the syllabus. 9.4. Yeah, so here they give you a function yt, which is defined as yn times the pulse function, and they also give you that yn is 0.8 to the power of n if it's between 0 and 5, and 0 otherwise. And then for a, for example, they give you a pulse function that says 1 if t is between minus 0.05 and 0.05, and 0 otherwise. So what then happens is you first sort of check for your already existing function. You check, okay, if I fill in the range from 0 to 5, because that's the range that the function goes in, what will be my outputs? Well, that's just creating a table, filling in the values. That shouldn't be hard. And then what you do, you multiply it with the pulse function. So let me just... I have this written down somewhere. Yeah. So what you can do then, and there's this formula for it. There are always formulas. Well, and let's just use y in this case, because that's what we were using. The new y will then be the sum minus infinity yn t minus n ts. Well, in this case, it goes from 0 to 5, because that's the range for which yn works. And in this case, you also know that, I think that was given in the exercise. Should be given in the exercise that you know. Yeah. TS is 1 over 10. So then you know that TS is 1 over 10. So you also know that this will then be written as, sorry, a bit ugly, but it's fine. Yn b t minus n over 1 over 10. Yeah. And what then happens is, if we go back to solution, you first get 1, and you know, okay, cool. So for, now I have to say it correctly. I always have to look at this for a second as well. You know that n in this case is 1, so you multiply with 1 over 10. So you know that this range from, let me see. Yeah, since this is the range from minus 0.05 to 0.05, you know that it ranges, since it's multiplied by 1, you know it's ranged from minus 0.05 to 0.05. And you know it's 1 because 1 multiplied with 1 because that's the value that's in here is 1. Nice. So then this one is 0.8, again just the one you calculated, and then you know that it's sort of by following this formula you sort of know that this shifts 1 over 10 to the right. So then you go here from 0.05, you know it then goes till 1.05, and you know that this is 0.8. You know this one 0.64, and then again you shift it 1 over 10 to the right. So that is how you can interpret pulse functions. They sort of change the function given. I hope that is clear about the pulse functions. Okay, again. Then the t-step transition probabilities in proposition 3.24 in the syllabus. Let me see. This goes way too slow. This is proposition 2.7. I have no clue what page it is, but we'll find it.
Somewhere in the 268.
Exactly.
Whoa. Insane.
Insane. Let X be a Markov chain with transition matrix P, then T is given that X0 is SI and SP. Will met this proof?
I think it's like about the shifting. Or
It's like the T transition probabilities in syllabus. Do we have to write one? Yeah. 3.24. Let X be a Markov chain with transition matrix. Oh, right. I think it's you make the transition matrix, and then what you can do is you can multiply it a few times, and then you get a different time, you know? So, like, I think what they meant with this, but I always use the other method of, like, the table method, you know?
Yeah, me too.
To sort of figure out at what time it is in the probability for what state. But I think what they mean here is that... Oh, wrong button. If you have a transition matrix like this with values and you want to, so this is T0 and you want to know, for example, at T1 or T2, let's say T2, at what time every probability is, you can multiply or do it to the power of 2. This is a way to do it, and then you have to sort of do it by hand. Or I think, no, your graphical calculator can also do this, I think. But,
probably.
you know...
I can't, but...
I can't. So this is, I think that's what they mean with the transition here. Because they always also say that...
Yeah, and I think they also...
This.
So you can do this... so if you take like 2 steps, then you can use that matrix to the power of 2. So also if you start from T4 to T6, then you can also use the matrix to the power 2. That's kind of what they say here. That if you go from 0 to T, that's the same as going from S to T plus S.
Exactly.
Yeah.
So that is what they mean, but overall, I would just use the table method where you say like T is 0, T is 1, etc. Because
it's less complex.
Yeah, they are the same methods, and I feel like that one is always more clear because you sort of can put things to 0 and put sort of cross things out when you know you're not going to end up in that state at that given time. So that leaves a lot less computations for you. So I would always say use that method. But you know, it's up to you what you prefer. So I hope that answers your question.
I see that pulse functions was clear.
And could you also mention, okay, pulse functions we did. In example 3.7 in chapter 3 of the syllabus, they make a step from x0 to x2, but how do you know what the probabilities for that are? Because x2 only depends on x1, right, and not on x0.
Okay, let's see the example.
Let's see the example. I don't know this by heart.
No, it's in the lecture notes.
Ah,
We were there.
excuse me.
It's a bit up.
3.17.
I think it was also in the exercise.
Oh, that could well be. Let's see. Again, consider a problem, post an example. 3.3. We want to solve it in a framework of notation. Note that x2 is x2, x4 is x3. No. Moreover, but there is a problem.
Mm-hmm. Oh, yeah, and then they use that time in variance.
Yeah, do you see it? I'm still reading.
Wait. The question was...
Here.
But how do you know what the probabilities for that are? Because x2 only depends on x1 and not x0. So basically how these probabilities are derived, I guess. Let's see.
I think there's also a drawing of this one, right? Because that would, like example 3.13, I think if you go up. Oh no, never mind.
Oh, no, okay.
Wait.
wait.
Was right there.
Oh, this is the... I was looking for...
Oh no, but it's the sunny thing one. So I think there is a drawing for it, but because I remember in the syllabus that they all went on over about the same problem. So I think
it's this one. Okay. Wow.
Nice.
Okay. Wait. Yeah. So it's.
And then the question is, they make a step from x0 to x2, but how do you know that for that r?
Oh, and because it's obviously only depends on the previous states. I think that's what she means.
So x0 is the initial one, right?
Yeah, but wait, where were we? 17.
Oh, the stream is loading. I don't know what that means.
So how they get the probabilities, basically.
Wait, hold up. 5 seconds. We have to. Where does it go in? We have to charge the laptop.
Technical issues. Oh, yeah.
Charging the laptop. 5 seconds. Yeah, that wouldn't be
Very close. No.
Okay.
Alright, we have power again.
Imagine if you just suddenly
left one by.
Okay. Let's go back. So, yeah, they want to calculate the probability that x2 is 3, given that it's sunny today. Well, it also kind of depends on x0 in some way, because... wait, how do I explain this?
Yeah, so I think from the initial probability, you're of course first going to compute timestamp 1. So I think that's your x1.
Yeah, indeed. So you need x0 to calculate x1, because x1 depends on x0, and then you need x1 to calculate x2. So it does only depend on x1, but you also don't know x1.
But x1 again depends on x0, so it's so you use both these steps, and you can do that, like I said. So this is what you asked a little bit before. It's about the t-step, so it's like really using the transition matrix. But the table again is just nice. And in this case, because I think, this is 3.18. Wait, hold up. Yeah, so they do it here, but you can of course also use the table to do it. And then what they did here is they first put in all the zeros to see, okay, we don't want to end up in that state, because we want to know, I believe for t is 4, we want to know only this value, and then you can start filling it in, and this is just a step-by-step guide on how to fill in that table. So I would say, if that's still somewhat weird, look at that. But yeah.
Okay.
I think
So, and they go in this example. So here, they go from 0 immediately to 2, because they use the transition matrix to the power of 2.
Yeah.
So maybe that's also a bit of the confusion.
Exactly, because if they only did so by doing the transition matrix to the power of 2, you sort of first do it to the power of 1 and then again, and so you sort of go through the power of like you go through the first t, but you sort of don't write it down. Like what I have with the lecture notes and the lectures itself, they leave out a lot of steps, but essentially they use x1. It's just they don't show it. So I hope that makes it a little clearer. I miss it the power 2. Cool.
Okay, that was it.
Yeah, it's weird because they
Great.
don't write it here indeed, but they sort of already did the power of 2 in this whole thing.
Yeah, so you don't really notice it.
Yeah, no problem. Okay, then. Okay, Sophie. Okay, thank you. I only still don't understand why in 10.18d they changed the bounds to 0 and infinity.
Okay.
Let's go back.
It's the...
It's the other
assignment,
yeah.
Oh, wait.
Yeah, I
okay.
passed it. 10.18d. Suppose actually then. Oh, this one. I think I know this one. Hold up. I made it all.
Oh yeah, it's a normal step function. So US.
Yeah, so in this case...
Wait, you had it here still, right?
Yeah, I'm writing it down again.
Perfect.
So we have minus infinity to infinity for US, because it's a little bit different, that's why I write it down again.
Yeah.
T minus S ds. And again, since you multiply these two, whatever the impulse response is, doesn't really matter. But as soon as this S is lower than is 0 or lower, this step function, this U, will never... it will always output 0. So then this is multiplied. So if this is 0, this whole bit will also be 0. So then it's sort of useless, I guess.
Yeah.
So what happens is we know that only for S is bigger than 0. Or also equal, I forgot. I think also equal 0.
Yeah, I think so.
Yeah, also equal 0. Then it outputs a value. Because then this will be 1 if this S is equal or bigger than 0. And then this bit will also output a value since it's multiplied by 1 and not by 0. So what you can do, since we know this must be the case, of course the integral will still be minus infinity to infinity, just the whole part from minus infinity till 0, that whole part will just be 0. So, and then you have an integral which basically just sums all the small boxes under a function, right? So then you have 0, 0, 0, 0 plus the bit where it actually does output a given value. But as of for now, this whole bit of the integral just outputs 0. So that is why you can in fact change the integral to make it from 0 to infinity and then just this. Because like I said, this minus infinity to 0 will only give you 0, so it won't really change anything from your final answer. So that is why you can change it. I hope that is clear as well. Let's wait, because I see on the screen and I'm still explaining it on stream, so let's wait a bit. Also, did we answer all questions now? Because if we skipped some people, let us know, please. That'll be sick.
Let me check. That would be really sad.
Okay, I get it now, thank you.
Okay,
yes,
that's
cool,
great.
cool.
I don't think we skipped anyone.
Cool, that's nice.
Cool. Okay, let's see.
Are there any other questions?
Insert lift music.
Elevator music vibes. Or maybe an exercise that you want to do with us, like an exam exercise, not that I have done all of them, but we can try. Or any other questions, exam related. I'm all out of questions. Well, it's great that you asked so many, Laura. That helps your current or your other students as well. So, nice.
And I guess it's a good sign if you don't have questions. after you. No, I mean after you all already ask questions, because like sometimes if you don't have questions, it's because you didn't catch it at all.
Yeah, if you get any questions when this crash course or Q&A thing is over, you can always ask on the Discord. Or what's at least I'm.
Yeah. I am basically free after Wednesday, so you can just harass me whenever you want.
Nice. Yeah, so we're always open for questions, even if you don't have one right now.
Yeah, we can maybe do that question from the exam that I...
Oh, yeah, right.
Yeah, because during my work group I was doing this exam, and I got stuck on a question, and we can do it again, because
we figured it out. Yeah, maybe it's nice, because I'm not sure if the person that asked the question is currently here, but...
I did see him.
Oh, you did see him? Okay, but else if they watch you back or something...
Wait, where is the...
this one.
Yeah. The exam. It's
slow. Have some patience, girl.
Patience, it's not my second name.
Old exams.
Wait, yes. This one. And we can just do it again, so the other people that are watching also know what we're doing.
That would be nice.
Yeah, it's this question. So they're giving 3 systems.
Yeah,
we don't
system.
No, we don't know if they're
LTI.
Right.
Right.
So that's the whole thing. And then they give these statements about it. And then you have to determine which one is not true, which can be confusing because they use the things like T1 is not an LTI. So, but we can walk through it and just for every statement, like, check whether they're true or whether they're not true. So yeah, we start with 1. Let me get my notes, so I'm sure that I'm not gonna do
do it wrong again.
Anything confusing. Where are you, Daphne?
I am here.
Yes. Yeah, so the statement is T1 is not an LTI. So how can we check that? We can check that by determining whether T1 is linear and time invariant, because that's LTI stands for linear time invariant system.
Yeah, so overall, if you're asked to check if something is an LTI system, do the 2 following things that Avi is now gonna do.
Yes, okay,
Rule
so
of thumb.
let's tab and then go here. Let's go. Here's some space. Okay, so from memory, I think T1 was xt plus 1. And then...
You can't see this now because of the webcam.
Oh,
Oh,
our
So
face is
you
in front of it.
you can scroll sideways.
Oh yeah, okay. That's smart.
Our face
Oh,
is not.
Where? How do we do that? It disappeared.
No, it's
Hold
not.
on.
Oh, okay. Cool.
Meow.
Perfect. Okay. And then to check for linearity, you use this formula. Oh, it's really long. Nice.
Write a little smaller.
It's
It's fine now, you can.
Next to the pens, the little thing.
The mouse with the...
Yes, that one.
Aha, okay. I'm such a boomer. Okay, so
Nice.
this is the formula for linearity. So let me write it down first.
Pretty long.
Nice, okay. So it's basically if you insert these 2 together in one go, is it the same if you do it apart? That's kind of what it says. And to check it for T1, you can we can omit the A's and the B's and we can just use the sum, because that also explains it. So we do this. we have an x1 and an x2. And this is then the input. And here it says the output for t1 is the input plus 1. So that's what we do. So this is what this would give. And then for the second part, that needs to be equal in order to be linear. This becomes the sum. And then you can already see that here we have input plus 1 and here we have input plus 1. Nope. So here it's x
Plus 1, girl.
Oh, yeah, sorry. I was already thinking ahead. Oh, okay.
No, it's fine.
Okay. So here you can see it's the x1 and x2 plus 1. And here it's x1 and x2 plus 2. So here we can see that this is not linear. So...
yeah, not an LTI system. That's basically what you already
Yeah.
can conclude here.
Exactly. So now you already
Oh, you have to...
press the whole one.
You don't
You
have
can
to...
just
you
let
don't-
go.
Yeah, you don't have to click it.
okay.
It's fine.
Yeah, so it's not linear, so we already know it's not an LTI. So we know this is true, but unfortunately we need to check which one is not true. So for B, the question is the inverse of the second system, if that is equal to taking the derivative of the input. I don't think that was true in this case, because I think it would have been if this was to infinity, right?
Wait, sorry. But no, but this is true because the last one wasn't true, right?
You're so smart. Okay, sorry, I forgot. But
Yeah, so it's...
oh yeah, it's just it's I confuse myself on the daily.
It's fine. No, so essentially what they asked you was to check whether T1 is on the LTI system, and then the question was, in your group, what they asked you was whether why T3... Because the final answer of this question was the third system isn't an LTI system, so D is wrong. And they asked you why that was again.
Yeah.
So-
Yeah, but I thought we can for the others show the
Oh,
whole
sorry.
thing. Yeah.
I mean, you
But-
can. That's fine.
Yeah, we can skip to the last one because I think there's some other questions too. So,
Yeah.
Okay. Then we show why T3 is not an LTI.
Exactly.
So confusing.
Because then you can also show the... not the linearity, but the time and variance thing, because I think that's useful for them to know.
Yeah. Can I erase this?
You can go down, scroll down.
Oh yeah. I'm so smart.
It's alrighty.
Okay. So T3 was.
Make sure we're not in the webcam in a bit.
It's
Oh yeah, smart. I think it's okay now.
Yeah.
Wait, let's check if that was it.
Nice.
Yeah, that was it.
Oh. Girl, what are you doing?
oh, you pressed Windows instead.
Oh.
of It's
Oh,
fine.
okay.
No, you're good.
Now we're good.
Or- What do you want?
Yes.
Sorry.
Okay. Perfect. So first we check
Okay, you look.
the linearity. And oh yeah, and it is linear, so that's what we will see now. If you have two inputs in this system plus x2, this will result in this again, so hope. Oh, times ut. So because this is in between brackets, both x1 and is times ut and x2 is times ut. And then if we do it apart, plus this, then it becomes plus x2 times ut. And yeah, that's the same. So that's why we can conclude that it's linear. And I think that was where I got stuck on last time.
Yeah, exactly.
Yeah, so, and now we can show that it's not time invariant. Yeah, and that was in the answers. So we can just show that. Let's check. Yeah, so T3 is not time invariant because if you give us input... Wait, what is the formula even?
Yeah, first give them the formula.
Yeah,
else
that's
it's-
maybe smart, yeah.
It's a bit of weird.
Yeah. Okay, so the formula for time invariance was...
Yeah, so basically what Avi is writing down this formula, basically what you do is you check whether if you shift the input of the system, will the outputs shift also. That's to check whether it's time invariant or not. So that's the formula, and in this case you can fill in any shift you want. And so here, I think they did it with the delta.
Yes, so they shifted the delta, and you see that if it's +1, then it's 0, while if it's -1, then it is just again delta t minus 1. So if it were time invariant, then this would also be delta t plus 1.
Yeah,
Yeah.
but it isn't, and it is true. That is because
And that's because of
Yeah.
the step function again. So if you input something with t plus 1, then the step function will become 0, and that's why.
yeah. So what delta does, delta only outputs a value if whatever is inside of it is 0. So if you have delta t plus 1, you know that t must be -1. However, if you know that t is -1 and you plug that into the step function, the whole thing will result in 0 because step function.
Yeah, I think that is because of that's like this property that if you multiply a function with a Dirac delta, then it becomes...
Second one is an F or delta?
Oh, yeah, sorry, that's...
No, it's fun, it's just for...
Yeah, okay, wait, this is an F. So, then it's... I do it again.
You write your F in a very specific way.
Yeah, okay, wait, it's an F. Then it becomes this, and then still multiplied with that...
So
blah, blah, blah.
I feel like this is a very useful function to know for your exam. Like,
so,
write this down.
Yeah, so the U became t plus 1.
No, yeah.
Oh,
Yeah, that's how you can see it.
yeah.
Yeah, so if you multiply ut times delta t plus 1, then the shift goes towards the u, so it will be that. And then you know that t must be -1 in order to make the u correct, and then it doesn't work anymore.
Yeah,
so that's
I
how
hope
that...
that was clear.
Yeah,
Yeah,
how
so
that
for the
formula
people of my work group that I failed. So this was the answer that I was supposed to get.
Yeah, so that was sort of an intermezzo for Indeed Your Work Group.
Yes.
I saw that Laura asked, could you maybe explain exercise 8.13 again, because I don't understand what is happening there. We can.
I think that's the one with the pulse functions.
No, it's the one with the partial integration. Ooh.
Oh, yes.
That's also a useful formula to put on your exam sheet or your cheat sheet, by the way. The partial integration. Like, I don't think you'll be needing it because it takes quite a lot of work, and in the exam you don't have to write like very long
You never know.
integrals,
Maybe,
but you never know, indeed.
yeah, maybe they'll do less questions in partial
What
integration.
assignment was this again? Assignment... Am I blind?
Yeah.
1.6, yeah, but is it like 4?
Oh,
right.
you didn't write it down.
No, for some reason I didn't. I think it's 4. Yes.
Yes, so good.
Alright, so it's 8.13.
Yes.
Oh, here. The function xt is plotted below in the interval. Oh wait, then I also have to go to lecture notes and go to chapter 8. I think I have written down the page number. Yes. Oh, pretty close. Now I can just scroll up. It's
Wizard.
13b here. Yeah, so this was indeed a very, very weirdly sort of stated question, and I don't think they'll make it this fake on the exam, but you never know.
You never know.
So we have a periodic function xt with a fundamental period t0 that satisfies this constraint, and it can also be written in these following orders. And they first ask you to sketch xt for minus 2 pi t to 4 pi. Mention the relevant values. Well, this is sort of a way to see, are you reading this question very carefully? Because here they say that the function satisfies that xt is equal to t. And you know that xt equal to t looks like a function that goes like this. They also say that it must be sketched between minus 2 pi and 4 pi, and we also know that the period of the function is 2 pi. So you know that every 2 pi, the function sort of repeats itself. So what you get is a zigzag line, basically. Very pretty.
Wow.
And I think it was supposed to be plotted from minus 2 pi as well, so it's here.
And then till here.
These lines, you don't necessarily have to plot them. They can be sort of the dotted lines as well, but it doesn't really matter if you draw them either way. So let's say this is minus 2 pi, this is 0, this is 2 pi. I drew too much, but that's okay. You didn't have to draw this bit, but it's fine. Alright, so that's how you can plot this function for question A. Then B, determine A0. Let's see. So normally you could determine A0 if you have this formula by looking at the spectrum and seeing, okay, what happens if we fill in 0 for the fundamental frequency, or sorry, for the K. Beg my pardon, for the K. And then if you fill in K here, this whole bit becomes 0, which means this whole with the E becomes 1, and it's just the thing that is in front of the E. However, in this case, we don't have a spectrum and we don't really have values, so that's sadly not possible. Luckily, there's also a formula for A0, and again, write this down. So we have A0, which is 1 over T0, 0, T0, xt, dt, and for completeness sake, I will also write down AK, another useful formula.
And when you've written that down, there's also something useful to remember about A0.
Yeah, I have it here. I will go over it. if I'm thinking the same thing you are.
Probably.
Alrighty. T0, xt, e, minus e 2 pi over T0, K times T dt. So these two formulas, write them down, very useful. And since we are going to take the primitive in a bit of this whole thing, since it's in an integral, I would also write down what the primitive is of this bit, because we always use this bit, always. So it's useful to already know the primitive, so that you don't have to think about it on the exam again. So I will also say that the primitive, I would just put it on your cheat sheet. I did that last year and it helped me, so. The primitive of e minus I 2 pi divided by T0 K times T is minus 1 over I think it's also in the slides somewhere, but you know, it's useful to have anyway. K and then E minus I 2 pi T O K times T. Of course, you can derive this by looking at, okay, this stays the same for E, and then to sort of cancel it out in your primitive, you can divide that whole bit by 1. It's basically the same, but, you know, it's always useful to have it. Alright, so now that we know these formulas, again, useful, write them down. Oh yeah,
And
there is another way. So okay, let's go first. So
Yeah.
A0 is now asked of us, and so you can of course use this formula. I personally used it myself because I find this way more logical. But then I'm
I
sort of
always use the other method.
yeah, I'm sort of mathematically inclined, so I like the integrals. But if you don't like the integrals, which I can understand, A0 can also be seen as the average over one period.
Yes. So
Right.
the average under the area under the curve.
Yeah,
over
so
one
the
period.
average of the area under the curve. That's the average.
Just the area under the curve for one period, right? Is that the average? Okay. It can be.
I always learned the average. Wait, hold up. Where's the function? Here. It's like the dotted line.
Oh,
And that's the average.
but that's also the area under the curve.
Oh, right. That is the area under the curve. Yeah, you're right. Yeah, so...
Okay, so it's both, I guess.
Yeah, so the average over one period, or indeed what you said, the area under the curve, can also be your A0. So then you just want to know what the area under the curve is for this one period. Spoiler alert, it's, I think, pi.
Pi,
Yes. But if you like formulas like me, we know that T0 was 2 pi, so you can say 2 pi from 0 to 2 pi. And then xt was t, dt. Is this going in my face? I think so. Let me go down up a little bit. Yeah, now you can see it too. And this, of course, wait, let me just go write it here. Which was so we had 1 over 2 pi 0 2 pi t dt. And now we take the 1 over 2 pi. We take the primitive of t, so it's 1 over 2 t squared. If I'm not mistaken, nope. And then it goes from 2 pi to 0, which will be 1 over 2 pi. And then we are going to fill the values in. So first we get 1 over 2 times 2 pi squared. Be careful, this whole thing is squared. And then minus 0, because, well, you plug in the 0 here and it all cancels out. Which then is 1 over 2 pi. And then the 1 over 2 times 4 pi squared, which is 1 over 2 pi squared, which is 2 pi squared over 2 pi. And now you see you cancel out the 2 and you cancel out 1 pi, so you get pi as answer.
Wow.
So that would be A0 in our case. So then we have answered this question.
Yes.
And now they want us to compute the AK for case unequal to 0. And they already give the tip, use partial integration. Now, like I said, I don't think they'll do it on the exam, but just in case. I will write down the formula again. So we have AK is 1 over 2 pi 0 to pi. That was T0, but we already knew that. Xt was just T times E minus I 2 pi T0 K times T. Oh, sorry, this was also supposed to be 2 pi. And so you see this cancels out, so we can just ignore it. Alright, and now the integration by parts is...
Oh, and dt.
Oh, sorry, I always forget dt. Like, if I don't write it down, but we're still using integrals. Bear in mind. So, right now we can use partial integration. And the partial integration rule is as follows. It's the integral from a to b, doesn't really matter which one. U times dv, where d is the derivative, is uv minus v du. Alright. In this case, we can choose which bit of this will be the u and which bit of this will be the v. But mostly you just, let's see, we say that t... Wait, why is there no call? Well, never mind.
Color denied.
This bit is u. I'm using the colors to make it more readable in a bit. And this one is v, because since you put this one on v, you know that this is already the derivative form of v. This means that since we want v in a bit, we need to take the primitive of that derivative. And well, the primitive of this one is also easy, but this one, if you need to sort of derive that later on again, it's going to be an absolute mess.
Yeah,
And
because we want that to be the u because of this.
Exactly.
Yeah.
And we want the u indeed to be the
Should be
dt here, because then this will be... Jeez.
To make everything a bit...
Sorry. We want this to be dt in the end, indeed. So that's why we choose t to be u and v to be this whole mess. So what we can then do, now that we know how we're going to partially integrate, we can say, and this is going to be intense. So we had this. So ak is 1 over 2 pi. That just stays the same. Now we're going to follow this bit. So we say minus I 1 I k e minus e k t. That is in fact the same formula as this one. So, but now the 2 pi is gone, so it looks a little bit different, but it's actually smaller. Times the t that we already had. So this one, e. From 0 to 2 pi. Alrighty. Minus the integral, so this was the first part. That's this one, and now we're looking at the second part. V is minus 1 over ik, because now it's the how do you say that, the primitive of that bit again.
Mm-hmm.
E minus ik t dt,
Yes.
where
And
t is now the u. Yeah, and this was 0 to 2 pi.
Perfect.
Yes. I won't bore you by working this all out, because I think that's a bit too much of the good details, but this eventually...
3 pages further on.
Yep. It eventually boils down to minus 1 ik plus 1 over 2 pi. If you really, by the way, want to see this worked out, please text me and I can send you the details of this. Which is minus 1 over ik, which I would find a suitable answer, but for some reason in the workout section they also wanted you to sort of work the I out of this.
To write it even shorter.
To write even shorter. They didn't specifically ask for it, but they did do it in the final workout, so then we do that as well. Another useful thing to know, I squared is always minus 1. Don't forget. I see a lot of people that text me, Daphne, I don't understand something, and then it's just minus 1.
Yeah,
oh, right.
The I disappears.
Yeah, so it's...
Just write it on top of the cheat sheet.
So this would be the work round for 8.13c.
Mm-hmm. Oh, and then, D was kind of...
Yeah, D is kind of weird. It's sort of... how do you say that? Like, I don't think they will ask you that kind of question on the exam, but who
we'll
knows?
Explain it anyway.
Exactly. But what they want you now is to sort of compare these 3 functions together and see how they relate to each other. So here they ask you to determine B0 and B1. Well, in this case, if you would write out this sum, if you would write out from minus infinity to infinity, you will get this whole sum with ease again, the same way as you would write out a spectrum. And you would have that A0 is the single value that stands in front of that whole sum that doesn't have an E with a power, with a frequency with it. That is very similar to this B0, where it starts in the positive direction. So, you know that B0 can be the same as A0. And since we already computed A0, well, very nice, then B0 is literally just also pi, because that was our A0. So this was just a question of, can you look at these 2 functions and see how they relate? B1 is a little bit more tricky, because they want you to compute B1 sine t. I think that was the function that they wanted you to compute. And you know that since this only goes from 1 to infinity and this goes from minus infinity to infinity, they sort of don't put the negative values in here, but here they do. So what you can say that this is the same as ETI plus a minus 1, the negative counterpart of that, E minus TI. Well, then you can work this out again because we know that it, AK must, you can either use this one or this one, and then you can plug in the 1 and the minus 1. So in this case, I did this times 1 ETI plus minus 1 I minus 1 times minus 1, sorry, E minus TI, and then, well, again, I won't bore you with all the simplifications, but you can rewrite it eventually as this to make it one fraction, to E minus TI divided by 2I. Alrighty. And now it's something that you should sort of see after practicing. No, Lara, I know, like this one was very...
Yeah,
you had to see it, and honestly, I had to look at the exam, or like the
exercise.
the answer module myself a few times as well, like, wait, what are they doing?
Yeah, same.
So, don't worry, I don't think they'll ever do this on the exam.
That would be like...
A good thing to note, because, this was a bit fake, but this is a thing that you should see eventually. If you put this together, you see that you have ETI plus E minus TI. And then you should sort of think about, inverse Euler incoming.
Mm-hmm.
So we can work this out to be TI minus E minus TI divided by 2.
2I, yeah.
Yes.
So that's already, you can see that it's from the sign.
Yeah, exactly. Yeah. And then you know that this is minus 2 sine t, because this is the sine version of the inverse Euler. And then you know by
but
this...
it's also a half should be somewhere, right? So the 2...
That is already 1 over 2.
Oh, yeah, sorry. Yeah, my mistake.
Why can't I?
So good.
Okay, it's sort of... My Control C is not working anymore, but...
Top right,
Yeah.
maybe.
That's fine. Okay. So you know that from here, we know that B1 was supposed to be minus 2.
Yeah.
Because we had this, and we worked it to a form of this. Again, this is a bit of a fake exercise. I think the most important takeaway from this is that you can work out fractions into ease to make sure that you see an inverse Euler, or I don't know, what more do you have? Like you have all these, with the Cartesian and the polar form, it's really a matter of seeing, can I convert to one of the two forms to make it more easy for myself? And if you are stuck at a certain exercise, always think about, hey, if I put it to a Cartesian form or to a polar form, can I use that in any way? Can I sort of change these values around? And I feel like, because a lot of people tell me I don't see that, and unfortunately the only answer I can give to that, practice a lot, and then eventually you'll see the steps. But that's
also why, because I didn't really point that out when I was explaining the frequency spectrum, but that's also always why you have a middle where the 0 is, and always minus and plus at the same locations, because it comes from the same cosine.
Yeah.
And then when you rewrite it, you get one E with plus and one E with minus, and that's how it's mirrored.
Yeah, exactly. Another useful formula that I just saw on my sheet that I think is useful. If you ever have E minus I k 2 pi, whatever this k is, this k can be 10,000 for all I care. But as soon as you have a multiple of 2 pi in here, you know that, because we're basically looking at a unit circle, right? So you can go round the circle and round it again, and this round always is 2 pi. So the same here, just constantly doing 2 pi, sure, that's great, but we don't really care about that. So eventually you will still end up writing this as sinus minus 2 pi and cosine minus 2 pi if you're converting it back to the Cartesian form again. And this is 0 and this is 1. So you can write e minus I k 2 pi. Whatever k is, you can write it as 1.
Yeah.
That's basically another... Like, I think in one of the slides he called it the mathematical beauty or something.
Yeah, he was really,
He was
really
very
amazed by it. He
Yeah.
loved it, yeah. So, yeah, usually the k is, like, hidden because it's multiplied by the 2. So
Exactly.
So you see, like, 300 pi.
Yeah.
And then you can just check if you can divide 300 by 2.
And if
and
you
then
can,
yeah.
yeah.
So then you know it's...
Exactly.
Yeah.
So that's another useful thing that you could write down if you want.
Yes.
Alright, I think that's the answers to the question. I don't think there was a E. No, there wasn't. Okay, cool. Yeah, you had to draw it, but did they ask you to draw it?
Yeah.
But you know how to draw a sign, I hope. And you have your graphical calculator, so you don't even need to know it. You can just plot it.
Yeah.
Nice.
Love that.
So yeah, I think that's all for this. Are there any more questions? I'll also wait for the delay.
Gezellig.
Love it. Thank you so much for all the explanations. Praise the Queens of Math.
Oh, cute.
Very cute, very cute. Thank you. Yeah,
Yeah, I think if there's no more questions...
then that was it from us. We'll wait a little bit longer, like 5 more minutes, if
Yeah.
something comes up. But like I said, if there are more questions even after this, don't hesitate to contact any of the TAs. We're here.
here. We support you.
Yeah.
Also just for mental support, you know. We're there.
Whole therapy session. No. Nice. Okay, no problems.
No problem.
Then I think if there are no... We'll be here for like 5 more minutes, but then if no more questions arise, then we'll stop and...
Say goodbye. This is the end. Or else...
Nah, we still have to reset. No,
Yes.
JK. It will be fine. Alrighty.
Alright.
I think that is it. Good luck with the exam, guys.
Yes.
I forgot to say that.
Next week, then.
Yes.
That's nice though, because you have the whole weekend. You don't have any exams.
You can just die for applying
Yeah.
that. Love it.
Same. For real.
Mm.
Every tentamen a week, I die a little inside.
It's fine.
It's fine. No, we're all good. Mental health first, guys.
Yes. Alrighty, then I think we're going to say goodbye.
Yeah.
Thanks for your attention, and Thomas, please enter screen because I don't know how.
It's-
Oh,
It's a
yes.
big red button. Okay.
Bye.
Well, bye guys.
Not yet. And.